Okay, name's Fraser. We started working in this space, looking at data integration, data fusion, probably Bruce Dixon primarily, but in the mid to early 80s. Essentially, GIS system just came on the market, and I think I put the first ARC Ingress into CSIRO. But we started to realise we had lots and lots of data. We could collect it. GIS systems were fantastic. They made you think how to put the data in, integrity, all that sort of stuff. But what the hell do you then do with it? So what then happened was at about the mid-90s, or early 90s, we put up an AMIRA project, P491, and it was looking at the integration of satellite information with radiometrics. Bruce was an airborne radiometrics geochemist, quite a good one, and I was involved in satellite remote sensing, looking at ion oxides and distinguishing things. And so this slide is actually quite pivotal. It's an area north of Rocky called around Marlborough. And on the left there we have our radiometrics, KUPH, and on the right we have just a hematite goethite ion oxide draped over our elevation model. And we thought we could see patterns in there. I hope you can too, maybe you can't, but we thought we could see patterns in there. But there was no technique that we could use around that actually enabled those patterns to be well defined. So as a consequence of that, we then decided to run an AMIRA project that we then looked at about 30 or 40 different techniques. All sorts of standard image processing, LS-FIT, you name it, principal components, directed principal components. And the long and the short of it is, as part of that whole process, we came across this weird technique out of Finland called self-organising maps. And we looked at it and sort of said, oh, that's interesting. And that was the beginning of the developing the, how do I say this, the self-organising maps hammer that we now nearly apply to lots of different things. Just acknowledge there as well, I mean, Bruce is not here, but Bruce was pivotal in developing this whole process. Peter Kowalczyk, at the time, we did a lot of work with him at Osborne, and that also was very pivotal in pushing the technology. And lastly is Max Lee. Max is the geotech, used to be in ACM, sorry, AMC, but he's now, I think he's a prof down at Monash already. And, but he was also pivotal in getting this work into geotech applications. Okay, so self-organising maps, it's a method of data analysis based on principles of vector similarity and turning everything into a vector. It was developed by Teivo Kahunen in about the mid-80s, that's when he first published on it. And it essentially, he developed it to counter neural nets, because people started to have desktop computers at that stage. IBMs were just out, and everyone was starting to look at how they can analyse data using computers. And, but he didn't like neural nets at all. And there was a whole lot of reasons for that at the time. Most neural nets were supervised. He didn't like supervision. And he just thought it was a bit over the top. So SOM can be used for both exploratory and confirmatory data analysis investigations. If people, just understanding what a data set's like, and then once you've developed a model, being able to prosecute that model going forward. There's a philosophical thing here I'll mention in a minute. Whoops. The other thing is, there's a debate amongst the statisticians, and I'm not quite sure how many geoscientists will be impacted by this, but maybe some mathematicians. There's a big debate as to whether or not you're a frequentist or a Bayesian. And this is to do with statistics. And I think this is where geologists and geophysicists have to have a really strong look at themselves. Because anyone who's saying they're a geologist and they're doing Bayesian techniques, I'd go back and start reading some literature. Bayesian techniques tend to be supervised, which means priors and the like, which is fine. But the reality is most geology, if it hasn't happened there, it hasn't happened there. So the probability of it happening there, given the fact we've had 4.6 billion years of time, roughly, and depending what sort of you're actually looking at, up to 4.6 billion, frequentist approaches are much better, much better. The reality is that they're very similar and can be treated very much the same way, but it's philosophically, I think you've got to put it in your head. I'll stop preaching soon. Okay. Essentially, on the left there, we've got a number of techniques, and on the right, we've got what we want to get out of the data. And there are techniques that are really good for doing particular operations, like clustering, classification. There's a big difference between clustering and classification. Associations, finding how your various variables impact each other, and other. Can you, rather than collect, say, 40 geochem assays, can you only collect 20? And so therefore you collect the 20 critical elements as opposed to 40 that the other 20 that don't really do anything to your analysis. Imputation and prediction is a really big area in geosciences. Most of our data sets are incomplete, so therefore we've got to impute, we've got to predict, we've got to have methods that will cater for null values. Looking at linkages between data sets, so you've got speciality techniques, but the reality is SOM, self-organising maps, can basically nearly do all of that. It may not be the best technique for doing things, but it does a lot of those things very well. Essentially, the first third of the talk is going to be on the actual way SOMs are made visually, and the rest I'm just going to run a whole string of examples. And some, I've given this for a long time, we've talked about this. I'll put some new examples in, but if you heard some before, I apologise.
Steve, can you explain the difference between supervised and not supervised?
Okay, supervised is when you know what a cup looks like or a tree looks like, and you know the characteristics of that, then you go looking for that exact thing again, that exact shape, characteristic, colour, morphology, whatever. Unsupervised is you just go into a data set totally blind, without any prior conceptions, and say, data, tell me what's in the data. And if you get something that comes out that looks like that, you say, well, it might be a bubble. But that's the prime difference there.
Presumably, if you supervise, it could be faster too.
Oh, yeah. But the problem with the prior or is how good that prior probability that is. And unless it's, depending on, again, what sort of fuzziness you've got in there, etc., you'll miss things. You really will miss things. The idea, what SOM and way I typically work at it as a first step in an exploratory mode, is you let the data tell you what's in the data. And then once you see the patterns in the data, you say, hey, that looks like a tree, or hey, that looks like a VMS deposit, or hey, that looks like a geochem anomaly of some description. So that's sort of the game that I play. The other thing is you look for outliers, because outliers are really important, especially in geochem, but even in geophysics.
Sorry if I can. I mean, it's a differentiation between one providing hypothesis, providing a constraint to meet that hypothesis, rather than having a totally open set like you're suggesting, which enables you to actually then infer based on the result of the analytics, which is again the position we play very heavily in psychophysical systems as opposed to, I guess, first principles engineering models, where you do create a core hypothesis, build that model, constrain that environment, try to prove against it, and it ultimately is a less versatile approach.
Exactly. Yeah. I mean, a classic example of sort of people having blinkered view output on life is Outokumpu mine in Finland. Nickel copper mine, been produced for years, it's mined out, etc. Somebody actually went back and started looking at the tailings, and they came across these little clear bits of there's kimberlites intertwined in the Outokumpu mine, and they were never really recognised. And it's just an idea of somebody having a really blinkered approach, and now it's being reworked by the Geological Society of Finland to produce diamonds. That's the tailings. Okay, so how does SOM work? SOM takes there's a whole lot of yellow points there. Andy Green, who's next door, I joined North Ryde early 80s. Andy was one of my group leaders, and he had an approach that everything you could visualise, the best way to visualise it is through scatter plots. So what we have here is we've got a cluster of data points in XYZ space. And what SOM does I'll show you how it does it, is it treats each one of those points as a vector, and then it finds a best matching unit or a node vector. There's that black line up the middle that actually represents that cluster of points. Okay? And it does that for every cluster of points in your data set. So this is how it finds the essence of the skeleton of your data. Okay. So it's a segmentation technique and visualization technique that allows you to explore relationships. It's based on principles of vector quantization and methods of vector similarity. There's probably about 30 different methods of comparing one vector in n-dimensional space to another. Things from the dot product, cos, the Euclidean distance, and the list goes on, and sort of combinations of those things. The whole principle of SOM is based on two algorithms. One's a competitive algorithm, finding the closest vector to another vector, and the other is a cooperative algorithm that updates all the vectors in relation to that input vector that you're sort of regressing against. We'll get onto that in a second. SOM can handle both linear and non-linear relationships and Gaussian and non-Gaussian data distributions. It can handle categorical information. You can put in a 0, 1 being a category. 1 if it's there, 0 if it's not. So you can start to do text mining using this approach. And the other thing is it handles nulls. A null is an observation, of course, that hasn't been made. But when you think about it, when you've got a vector, two vectors that are nearly parallel in n-dimensional space, you take away one of those dimensions, those two vectors are still parallel, or nearly parallel. So that's how SOM does its imputation. And it's probably the best technique that I'm aware of that does that. Or any of the vector techniques actually can do it. Support vector machines will do it as well. It accommodates nulls and sparse data, as I indicated. Now, the output of the SOM is this thing called the U matrix on the right-hand side there. But what we have in the middle there is we have a number of clusters with the best matching units now in white at the middle of each of those clusters. And conceptually, to go from the n-dimensional space to the two-dimensional space, you think of it as a bunch of flowers, with a whole lot of flowers drooping out of a vase. You just grab the bottom of the stems and you just move it upwards. And by doing that, you can actually you've projected onto the sheet. And that is the self-organised map. The colours there represent the similarity of adjacent vectors or nodes. So what we're showing here now are those white vectors in the middle, and they're being shown there as dots on the image on the right. There's a whole lot of tricks and that go into that, but that's essentially what's happening. Cooler colours here represent similarity between nodes. Hotter temperature colours here represent diversity. Now, that's exactly it's not the case in the next one. Now, for each node on the map, we can produce maps of all the input variables, and that's the next step. So in this particular data set, we've got 6 input variables. Geochemistry, we've got gold, silver, zinc, iron, copper, lead. And these are now coloured so that red represents a high contribution and cooler temperatures blue represents a low contribution. So when we go from n-dimensional space to our map, we maintain what's called topology, meaning that the relationships that are in the n-dimensional map, we try and preserve them on the two-dimensional map. So adjacent vectors or adjacent nodes are similar. Okay? And just to try and show that, if we take that yellow circle there, that group there, how I get a... I don't. And that's not going to work. Okay. Okay, see in the top, I've got yellow circle, and it's highlighted a gold population that sits there. And that particular gold population in the yellow has got relatively high silver, high zinc, moderate iron, low copper, and a range of lead. And you can see where that plots on the U matrix at the top. So these visualizations here are our component plane plots, and they are probably the most important aspect of self-organizing maps. They're really good for looking at the relationships between things and how things, different populations. We take the next one there, that red circle, we can see where it plots in the U matrix, and we can say that's a slightly elevated gold population with higher silver, low zinc, moderate to high iron, low copper, and low lead. And just to show how we maintain topology, those two vectors there, the cyan that I've just highlighted, you can see how it's close to the red, and it's a higher gold than the red. It has, again, elevated silver, low zinc, higher iron, copper, and lead, etc. So this is how you start to make your relationships using the self-organised map and look at things. Please.
I just have a question. So how do you know the red ones are exactly mapped onto that area of the self-organizing maps? I didn't understand that point.
Because you know their characteristics. You actually know what the, for the want of a better term, you know what the best matching unit vector is.
Okay.
And therefore, and you know where it sits.
Okay.
On the software we've got, it's all totally interactive.
Okay.
Because once you have a sample, it's tracked through the whole process. Okay, so that really is self-organising maps 101. I mean, that's the basic principles of it. And once you've sort of got that idea, I mean, it just opens up a whole world of opportunities, I think.
Steve, I must be missing something. I just can't see how that's helped me understand that geochemistry.
Okay, if we just take away all my circles, I think I can do. Okay, think of this as the total world of your data. And on that we can see probably, we have 1, 2, 3, 4, 5 elevated zones. So what we can say is that there's 5 gold populations on there. The first one I indicated here is an association with silver, zinc, average iron, low copper, and elevated lead. So what they are, they're patterns in your global data set, for the want of a better term. Your global data set being the data you've put in.
Sure. No, I appreciate that aspect of it. I just want to know where to drill the hole. It doesn't seem
well, you're just getting a bit ahead of yourself. Yeah. You see if it works on there.
Laser pointer doesn't work. No. So you have to use the PowerPoint laser pointer.
The problem is, yeah, I'm on the system. I mean,
The mouse should work on them.
Yeah.
Do you know how? Oh, is this mouse?
Yeah.
Aha.
Yeah, so now go down the bottom and you can turn on one of those icons as a laser
Yeah,
pointer.
the mouse is there now.
The mouse is there.
Yeah.
Okay. I was getting used to the duck. Chicken, the fowl. Okay, yeah, so we'll get into that in a second. At this point, normally see, geologists are thinking too far ahead. Normally the question is, how do you train those nodes to represent the data? And that's what I'm going to show you next. So what we do, the red crosses in the corners are the original data points, and this is a fictitious data set, of course. And the black dots are what we called our random seeds. These are vectors that we seed into the data that we're then going to train to represent the data. There's a couple of...
Yeah, there's a seat there. Seat there. Yep.
And there's 2 back there as well. Okay.
Sorry, Steve.
Okay, so the red crosses are our input data, the black dots are our initial random seeding, and that is literally can be a random seeding, or you can do it on an orthogonal basis. You can actually do an equispaced grid across there if you want to. Random seeds, I believe, are much better, especially if you've got data points that have nulls in them, that are sparse data. So, there's a two-step process to train the data. There's a competitive step and a cooperative step. And the competitive step at the beginning is what we try to do is we take one vector point, an input sample point, and we take a data vector, we look within a certain radius of that data vector to find the closest seed vector. We find that seed vector and then we move it towards that data vector value, a certain amount. So all those parameters you have control over. Okay? We then begin the cooperative step. We take another radius in the n-dimensional space. It's not really a circle, it's not really a volume, it's going to be a hypervolume of some description that all the points are equidistant from your data point in question or your node in question. We take that and we look at all of the random points that occur within that volume and we move them a certain amount in as well. And this is the beginning of the training process. And the next part of the process is, well, actually what we do that other people don't in some of their SOM implementations is our first training area thing we use, we make sure our volume includes all the data. So then what you do, that's all moved in. So this is a way of actually bringing all the data into a sort of a more usable volume, you might say, at the beginning. And this happens for every sample point, every sample point in the data. And once it's done it for every sample point, that's called one iteration. So by this stage now, we're up to iteration almost 200. Sorry. So we then run through, that's not 200 at all, I'm sorry, there's 200 samples. So iteration 20, 60, 100, 150, 300, 400, 550, 7. And as you go through the iterations, the amount of movement becomes less and less. And until you actually hit what's called stationarity. And really what happens is everything just sort of sits in its one place and just vibrates from one foot to the other, basically. So there's very little movement in the sample. And that there would then be our trained SOM. So what we use our trained SOM. There's no of our trained vectors on the edge of the data. It all sits within the data. So we don't have our nodes that are outside the data volume. But we do have some nodes that don't represent or haven't got real sample points close by. And that's fine. We can handle that. So that there is essentially how we train the SOM. Okay, the optimum point is when you reach stationarity. Vectors are unevenly spaced, etc. So that really is how the SOM works. I mean, I can show those on movies, but I didn't decide to bring them not as a movie because I knew we'd have Windows machines here. Okay, now if we just move on to some examples. Okay, this is a big data set we looked at for Geoscience BC. Something like 15,000 samples, 42 elements, spread over about 150 square kilometres, 150,000 square K. And we've run our U matrix there. The next trick we do on the U matrix is we want to, this is a classification or a clustering that's occurring, but then we want to cluster the nodes themselves to try and make domains in the data. So then typically we do a k-means on the input data. And K-means is good because you can actually get some nice, nice firm colours to show things. So on the left, we have a geology over the area, and on the right, we just have the samples coded by their K-means colour. And essentially what we've been able to do here is we've fairly well reproduced largely the geology map. Probably in a bit more detail, in fact. So just at that sort of scale, we're actually sort of being able to reproduce the lithological variation based on geochem. This here is our component planes for that data. You can see up the top there's two major populations of silver, etc. Same schema as before. But if we look at gold, we can see very quickly that there's actually 6 gold populations in this data set. 2 highs over here, sort of a couple of points in here, and 1 down here. So there's 1, 2, 3, 4, 5, and 6. And what we can do with this is we can then go through the data set and physically display the locations of the samples that are represented by those various K-means clusters. So on the left we have all the sample points, and on the right there we have our SOM map. So we've got a spatial map and our SOM map. And what we're going to do is we're just going to go through each of the this population here, and it's basically coming up in green over there. So we're just going to go through 1, 2, 3, 4, 5, 6, and we'll see the spatial location of each of the samples. And what's interesting in this approach is there is spatial patterns in there. And what we're looking at all the samples that occur in a given cluster in this case. I think that's up a lot there around Mount Pollock, if I remember rightly. So this then begins a way of actually starting to target to use SOM as a targeting technique. We're still not using the best way of SOM for targeting, and that's using what we call the quality error, the outliers. But again, this is a way of giving different populations and showing spatially where those populations occur.
How would this compare with just a plot of the actual gold itself, in terms of you're bringing other information in, focusing on the gold?
What this does is brings in their gold highs, but they're separated on the basis of all the other geochem. So you've possibly got a gold in regoliths. You haven't got regoliths, but I'd say a gold in glacials or something that's been reworked sitting in a particular unit versus gold that's not in glacials that might be separate geochemically. Might have an epithermal type deposit separated from a porphyry type deposit separated from an iron copper gold type of setup.
So it gives you potentially more contextual information.
It gives you more contextual information, yeah.
Okay.
And once you've got these sorts of populations, you can then start to take all those samples and break them down again, if you want to. The whole Geoscience BC report is quite a thick report, but it does explore a lot of the possibilities. So there's all sorts of ways of using it for targeting in that sense. Okay. This is some work. We've moved on from sort of quick spatial use. We have done other studies that relate, and the one in the book I've left out because of time. But you can start to relate geochemistry with alteration effects. You can start to see process occurring where you start to do a scatter plot of two elements, and you can actually start to see the process of mineralisation occurring. You can then start to use that to vector mineralisation. So that there is quite an opportunity there. But one of the things that's happened in geochemists' world recently is looking at heavy minerals in particular. And this is work we did with at Macquarie University here some time back now. But what we looked at was chromite compositions, and we were trying to look at petrogenesis of predicting the petrogenesis of the chromites, and just to see if there was some sort of relationship between petrogenesis and geochemistry. And we looked at various styles. We looked at lamprolitic chromites, kimberlites off the craton, kimberlites on mantle, lamporites. And there's actually more different classes than what's shown there. But they did start to break up very well. That's our component plane plots. And if we start just do a scatter plot, we run from kimberlites on continental crust up on the top left here. This is a plot of chromium versus aluminium, down to things like lamporite down the bottom. And that's only using something like 11 clusters. If we take the same data and break it up into something like, I think there's about 30 clusters there, just a bit bigger data set, we still see the same trend. And if you can remember, we put our labels on. The labels, in this case, were not included in the analysis. The labels we just carried through for visualisation. So we've got primarily our lamprolites down here, kimberlites on mantle down here, and kimberlites on crust at the top. So this is a way almost of being able to break out different styles of kimberlites in this case, based on the chromite composition. This work, I won't go into too much, but this work led to probably about 3 lots of different projects with 3 of the majors who were looking for diamonds at the time. Okay, getting on to a geophysical type approach. We're looking at SOM on volumes of petrophysical properties. In this case, inverted, and it was unconstrained inverted magnetic and gravity data at a place called Seagull in Canada, Seagull deposit. Location just north of the Great Lakes. And what the deposit is, it's a laccolith. It's an intrusive laccolith, and what we've done there is that's just what authors have done is they just draped the geology over the TMI and created a bit of an elevation display there of it. So there is, and the purple area there is the main area of the laccolith. And this is the input data for our self-organised map. These are voxel volumes of mag, sus and density. And we just ran the SOM on that to try and see patterns in it. And we broke it up using our k-means on that, and we've got these particular k-means clusters here. So what we do is we just start to pick nodes, shown here in purple, and where those samples belong spatially. So we can start to pick nodes and start to build up a pattern. And if we look at that pattern there, which is those 3 nodes up there, and samples belonging to those 3 nodes there and that node there, we get this sort of pattern here, which we saw in the original TMI data in here. So we can then start to build up our map and display all the nodes belonging to this here, and we start to see the outline of the laccolith. Include that, we see some of the infill type material on the top. And if you look very carefully there's actually a zone at the back here. Oh, it actually shows much better up there. We can actually start to see the feeder zone for the laccolith as well. So again, what we've done here is we're just by using the domaining of the SOM on the petrophysical volume, we've been able to just to bring in and create a geology map, and in this case the feeder. The feeder was actually a target as part of the process, the exploration team that was going on there. Now, at the very beginning, I mentioned to you that we had...
Sorry, in that example, do you have some understanding of what the relative contribution of the magnetic and gravity data are in that
we could,
assessment?
Yes, we could.
Because they may, yeah, okay.
But you know, I mean, what we've done here is we just domained it again. You can go back and look at the actual nodes and work out exactly what the contributions are. Yes. One of the things we look at quite extensively is this Q error thing. And the Q error is the distance. Lost my duck. It's the distance between a sample and the best matching unit. So things that are outliers will have a big QER error. In other words, this one here has got a bigger QER than, say, something here. So it's a measure of how a sample is not represented by the node. Okay. So this here is just all the QERs colour-coded and in plan view. And there's a slider across the bottom there, and I'm going to take the slider and move it across to the right and show less and less or higher and higher QER values. So moving across, we're getting progressively things that are more anomalous. And we're still in plan view. And we come to 1 pixel in this particular show here, an XY. And that green dot there, if you can see it, is the most anomalous pixel in plan view, sitting in here. If we now go to a depth plot, X versus Y, we can actually see that it becomes two voxels, or 2 pixels are represented by that particular thing. This is what I presented in 2007, in Exploration 07, and I was presenting it again in Perth a couple of years later, and a chap in the audience got up and said, "Looks pretty familiar, looks like something I remember." And he actually, that previous summer, he'd come from a drilling program over this deposit. And he was able to provide me with some geology. Now, if I just put that cursor on those 2, and that's the results of the drilling program. And there's actually a sulfide lens running down here. And I've never really seen this, I don't think, in geophysics before, where geophysics is actually that close to actually, this is a real predictor of a target. Sorry, Ken. but yeah, I mean, it's quite a good example of what's happening there. So this again is using this QER, this outlier approach to mapping anomalous data points.
And what was the data that was used to generate that?
It was a petrophysical volume of density and a petrophysical volume of mag-sus.
Okay.
From inversion.
No, it was a non-constrained inversion. Yeah.
But it wasn't the Seagull Lake example. It's another one.
This is
Oh, this is Seagull. Oh,
Yeah,
okay,
yeah.
okay. All right.
Okay. We often get people throwing us data sets blind. They say, there's a kimberlite in here, or there's a dipole, or there's something in here. And so this was one of those blind tests that we did. Again, we had susceptibility and density given to us. We ran through the same sort of procedure. We did our 2 component planes and then did our k-means on the right. And we then started to look at QERs, quantization errors. And I look, and these are very, very small quantization errors, and we start to get these vertical structures. And I sort of said at the time, I said, this can't be right. I was a bit embarrassed, actually. There's no way this was right. Start to look at it in plan view, and we had a cluster, which is the cluster of samples shown in green, whereas the purples there are QERs greater than 1.7. And I worked out there was at least 4 major targets, like so. There's no way this was correct. Plus a whole lot of subsidiary targets. And I was consequently told that we found those things that they knew about and could process by their own technology. We found pipes that they knew about that they couldn't find using their own current procedures. And they also found pipes that they didn't know about when using this technique. And this is over about a 10k by 6, 8, maybe 12k by 6k area. So I will move along very quickly now. You can start to do the same with our friends next door are doing core scanning, John Huntington, Kai Yang. And what we can do with this is we can start to integrate features extracted from the high logger, spectral features, wavelength position of ALOH, depth of the ALOH feature, wavelength of FeOH feature, depth of that feature, wavelength of the carbonate feature, MGOH depth, and then we put gold in there in our new matrix. And again, you can start to plot things up there. We've got MG feature versus gold, and you can see a trend. This is the colours of the Cambrian clusters. And I would argue that that is the process of mineralisation in our data set. And you can plot up, in this case, carbonite versus gold, and you see the same trend. It goes through the same colours. ALOH versus gold, same trend. So then what you can do, you can take those colours or take the samples and colour code them by the Cambrians on the actual drill stems themselves, on the drill holes themselves, and you can start to look at how things, you can start again to vector mineralisation. And in this case, we know from the people who gave us the data that there was a mineralised zone right through that middle there. So again, it's a way of using a combination of data fusion, for the want of a better term, what I call data fusion, not what other people, it's integrated data analysis to give you a target. We've applied it, moving on very quickly, microseismic waveforms. We've taken, you can take power spectra, code them by SOM, and this is what we've done for a particular mine. We've got 8 separate classes, and again, you can work out where those classes are. So this is an attempt to produce an automated classification and interpretation system for microseismics. Still a work in progress.
So the input is the power spectra, or
The input is the power
the
spectra.
power spectra, so not the time series.
Not the time series, yeah. Other technique here is this is near Kalgoorlie, KCGM, Mount Charlotte. We've done the same sort of a trick here. And we've got, this case, we've now got something like, I think there's a large number of, there's 24 classes that we've picked out. And the interesting thing here is the location, the physical X, Y, Z location is not included in the analysis. Okay? So we're just looking at the characteristics. A time thing was included in the analysis. There was a timestamp is included.
5 minutes?
Yep. So what you can do is you can start to pick particular, in this case we've got that, you can see hopefully as we move around. Again, what's really important here is there's a spatial coherence to each of the clusters. And it was not, as I say, X, Y, Z was not included. So it's actually being classified or being grouped on the other characteristics of the microseismic waveform. And I think the fact it's that spatial coherence that tells you that it's working. Okay. Another geotech example. We've got a whole lot of measured petrophysical properties. Geotech people tend to be very, it's a real art. I mean, a lot of it is very much an art. What we've been trying to do in this is actually put some quantification to their very qualitative, touchy-feely almost interpretations of things. So we have a data set that consists of 34 massive samples with known responses, 18 samples, blocky samples with unknown responses, and 8 massive samples with unknown responses. And what we're trying to do is predict how things are going to behave with respect to mining, or the stresses of mining. And the behaviours we're looking at are sugary, brittle, slabby and squeezing. And there's our input rock properties on the left, and there are our derived parameters from those rock properties on the right. And people will spend their whole life working out crack energy and how that relates to something. But once if we do not include the labels in the analysis, the whole thing breaks up very much into domains very neatly, as we've shown there. There's also other tricks, and I didn't really go into it, but you can project, when you're going from your n-dimensional space onto your map, you can project onto a sheet, a cylinder, or a toroid. And typically we do use a toroid, and toroids wrap. So in a toroid, your bottom wraps to the top and sides to sides. That's why you've got squeezing in all 4 corners there. we can then take do a principal components of the node values and start to look at relationships. And in this case, we have included squeezing, sugary, slabby, and brittle in the analysis. And you can start to see that sugary is related to a number of different parameters. Squeezing, related to crack length. Slabby related to shear waves per son and density, etc. It's then possible to go through and predict your unknowns based on things. And what we've done here is we've predicted our blocky samples in our unknown samples. It's the higher the value is to 1 is the predicted value or the predicted response to it. I'm afraid I'm going to have to move fairly quickly. I won't. Okay. Someone downhole geophysical logs. There's our raw PGNAA data. This is a neutron technique here. On the far left, we just have a geology legend, colour-coded, and on the column there is a geologist's log of a particular hole. What we did, we just ran SOM on this raw data to produce a geological map, and that's that column there. And you can see we did a very good job. Oh, hey. That's interesting. You can see here we did a very good job on predicting what the geologist saw, but we saw there's a unit here that the geologist didn't see. This is in coal measures, and you're looking at rocks types like mudstones, claystones, sandstone. They're very difficult to see, especially in a RAB type hole, RAB drilling. So that's what's coming out of that. Again, SOM for domaining, downhole geophysics. We have a geology. And again, we can produce fairly quickly. We can produce a synthetic lithology based on those logging tracks there. This happens to be a VMS in Canada.
Do you wrap up, Steve? If you can.
Yeah. Okay. Just really quickly. It can be done just on RGB images. And in this case here, I'm able to distinguish chalcopyrite and pyrite on images underground, which is very important for, say, metallurgical purposes. Okay, so I would say that SOM is really like a Swiss Army pocket knife. There are SOM approaches equivalent to most more traditional techniques. It does some things very well. However, most cases there's another technique that will do that particular procedure better. Okay. But certainly SOM is amongst best of breed for things like imputation, handling nulls, mixed data, and especially the visualization, because the output visualization can be really quite useful, and also for outlier identification. It's a computational tool for identifying domains within natural populations. It's exploratory, unsupervised and data-driven. The data tells you what's in the data. And allows mixing of all sorts of characteristics. You can start to put in all sorts of complex data types. And it really is an excellent exploratory first tool. And the ultimate goal is to convert our data to knowledge. Okay, so that's about it. But that was pretty rushed, I'm sorry. But